Hi everyone and welcome back to the channel. I know it hasn't been very long since my last video, which is a big change, but today we're going to be continuing on from Kepler's third laws and be talking about binary systems. Similar to last time, I'm going to be doing it presentation style, so I'll be looking down at my slides every now and then so I know what I'm going to be talking about. Right, so let's recap on the previous video. If you haven't seen that, I highly recommend you check it out. But we're just talking about all of Kepler's three laws, and we're going to do a recap on the third law over here, which states that the square of the period of the orbit of a planet going around the star is going to be proportional to the semi-major axis cubed, or the distance between the planet and the star. And you can see I've actually written out the full equation here. We've got t squared, that's the period squared, is equal to 4 pi squared r cubed, which is the semi-major axis, or the actual just radius of the orbit if the orbit is fairly circular, divided by g, which is the gravitational constant, and m, which is the mass of the big star that's being orbited. The way we came to this conclusion was very simple. I'm just going to very quickly speed run it. So we equated two forces. That's the circular motion force, so the centripetal force, mv squared over r, with the gravitational force, gmm over r squared. And then what we did was we cancelled out some terms and rearranged to get v squared equals gm over r. And then what we did after that was that we assumed that this orbit's going to be fairly circular, and so the distance that the planet's going to be orbiting in is essentially the circumference of a circle, which is 2 pi times this radius, or the semi-major axis. And so we can get a little speed equals distance over time equation from that and sub that into v. And then from that we can rearrange and go back to get back to t squared, and thus prove the third law. Now this is actually a very broad approximation for if the star and the planet, if the star is actually much greater mass than the planet itself. So that essentially you can say that if you added both the masses, this small planet mass is going to be negligible, and so you wouldn't even need to count it. You can approximate the total mass to just be the mass of the star. This is great for the Earth and the Sun, but there are some times when that doesn't really apply, such as, for example, Pluto and Charon. And that's when both masses are somewhat approximate, but not exactly quite there. Pluto and Charon are the obvious ones, with my interesting artist rendition of Pluto and Charon over there. So to actually give you a little comparison, Charon is actually 12% of Pluto's mass, and I know you might think that that's very small, but it's actually really, really big. For context, the Earth's mass is roughly 1,000,000th times the mass of the Sun. So that's when we talk about non-binary systems, so yeah, that's the right word. We're talking about really, really, really small percentages of the main star's mass. Whereas with binary systems, we're looking for, even 12% is quite high sometimes, but yeah, roughly that amount. What we need to consider when we're talking about binary systems is that gravity is an attractive force, and if you have mass, you have gravity. And it cannot pick and choose which mass it likes, so everything that has mass will attract something. And so this is one thing that we might tend to forget, especially when we're talking about things with really big mass differences like the Earth and the Sun, is that in actuality, everything has its own orbit. So what do I actually mean? Well, we know from just observations that we say that the Earth is orbiting around the Sun because it's the much smaller mass, but in reality it's more so orbiting around a center of mass, which, balances both the Sun and the Earth's mass. And you can see that I've put that there on the diagram with a little black dot. And you can also hopefully see that it's very, very close to the center of the Sun, but not quite exactly. So technically what's happening is the Earth is orbiting around this center of mass, which is essentially basically the Sun, because it's just very close to the center of the Sun. But also conversely, something that we all forget is that the Sun is also orbiting around this center of mass. It's just that this center of mass is so close to the Sun that it's basically negligible. But this isn't the case with binary systems, and that's what's most important. We call this sort of center of mass the barycenter sometimes, and what's important is that in this case this is not a binary system, and that is because this barycenter is inside the sun. So in the case of Pluto and Charon, what's going on is that this barycenter is not inside either Pluto nor Charon. And I've actually shown some really cool, one really cool GIF and one really cool image of Pluto and its moons. But you can see Pluto and Charon in the top GIF, which was made by Stephanie Hoover. And you can see that Pluto is actually orbiting the center of mass, and you can see the orbit as well, which is really cool because it's not something that we tend to imagine when we think about Pluto. We just think it's just stationary and orbiting around the sun whilst the moons are orbiting around it, but that's not the case at all. And you can see Pluto and Charon in the bottom image, which is made by NASA, ESA and others, where you've got the other moons as well, which are orbiting around in nice disks, because they're really tiny compared to Pluto, so we don't need to worry about them too much. But Charon, that's not the case. So I've drawn out Pluto and Charon in their nice orbits, and you can see I've marked the barycenter with an X. And what's important is that the X is outside of Pluto, and that's essentially what a binary system is. It's when the actual barycenter is outside of both planets, although sometimes some agencies can be a little bit more vague with what they define as a binary system, but in general that's what we usually adopt. This is important because we know that both objects exert equal and opposite forces on each other, gravitational forces, otherwise the orbit wouldn't be stable. And what's also very, very important is that they have the same angular velocity. This is really important, and from this we can actually get some interesting equations out of that. So if we label the distances from the center of each planet or moon to the barycenter, we'll say R1 is the distance from Pluto to the center, and R2 is Charon, and then conversely we label the masses M1 and M2 respectively in the same way. We can also say that the total distance between the two planets is R1 plus R2. So let's try and do a little bit of imagination here. And if we say that Pluto's mass were bigger, the barycenter would get closer and closer to Pluto's center, and hence its semi-major axis, that's the right word, would decrease. But conversely, Charon's semi-major axis would increase, assuming that the orbit itself, both the orbits aren't getting bigger and smaller. So what would happen is Pluto's mass would increase, Charon's radius would increase, and then Pluto's radius, not radius, semi-major axis would decrease, and then conversely it would be the same for Charon if they if its mass increased as well. So from that we can sort of figure out that the actual distance, the semi-major axes, are dependent on the fraction of the mass that its body is. So Charon's semi-major axis is dependent on how big Pluto's mass is compared to the entire system, and then conversely with Pluto's semi-major axis as well. So we can actually get two really interesting equations out of this, where we've got R1 is equal to M2 over M1 plus M2. So that's, which one is it? Pluto's semi-major axis is dependent on the fraction of mass that Charon is out of the whole system, multiplied by the total distance because it's a fraction. And then conversely the same with R2. But what's good is that both the distances d are exactly the same, so we can eliminate them and rearrange the equations and equate the two. So we get R1 multiplied by the sum of the masses divided by M2 is equal to R2 multiplied by the sum of both the masses divided by M1. And you can immediately see that we've already got some terms that we can easily cancel out and rearrange. So if we get rid of both the sums of the masses and then move the M1 to one side and the M2 to the other, we can get a very nice and simple equation that describes how the semi-major axis of each of the bodies depend on each of the other's mass, which is really cool. And then we can also adapt Kepler's third law for binary systems in this case. So we've got Kepler's third law for just, sun and earth type situation, t squared equals 4 pi r cubed over gm. But what we can then do is sub in d being the total distance. We can just say that is equal to r in this case, and we know that that's r1 plus r2. And then we can also sub in, rather than just the big M, we can sub in the total mass, so M1 plus M2. Now the reason being that we're subbing that into big M is because with Kepler's third law, we originally assumed that the planet's mass, or this little orbiting body, is so small that it's negligible. And so instead we're going to say, nope, it is now something that we need to account for, and so we pop that back into the equation. And so we create a new equation that describes binary systems regarding Kepler's third law, which is great. And then what we can also do, just for a sanity check, you can already see it on the slides, if we just say that, oh, one of the masses is negligible now, we can sub in that approximation and we get back to the third law, just the original one. So that's great. Of course, the universe is way more complex and amazing and has way more situations such as tertiary or triple or quadruple or sextuple systems where you've got multiple things orbiting each other because, like I said, gravity does not pick and choose. Everything attracts each other, everything orbits each other, and it all gets really crazy and way too complex for my little brain to understand. To be fair, triple body systems and multiple body problems are also a big challenge for even the professional astronomers out there. So I won't be going into that, but I really do recommend trying to read up on it and educate yourself about it like I'm trying to do. One example of this is the Algol system, where you've got Algol A, B and C. This is a triple system and you can see it over there with lovely nice blue image. Yeah, that's just one example of many where you've got more than two orbiting bodies orbiting each other, which is great. So thank you very much for making it this far to the video. Your prize is a very cool 3D rendering of Pluto and Charon orbiting each other, made by Tom Rouen on Wikipedia. I'll link to the actual image down below. Thank you very much for joining me once again. In the next video, I will absolutely try and do a nice crochet tutorial on something like the protoplanetary disks and whatnot. So I hope you'll join me with that. I'll see you soon.